Good morning, class. We'll be starting in the next 5 minutes. So I've shared the link, the YouTube link. Please share it with others that are not able to join here. So see you in the next 5 minutes, please. Thank you. All right, I'm with everyone here. So give me a minute. Let me get a slide. Meanwhile, those on YouTube, if you can hear me, kindly let me know, please. Please relax. Those on YouTube, I've not started. So I'll be recording now. Give me a minute. Okay. Those on Zoom, let me enable chats. So I will still disable it again. Are you notified that the lecture is being recorded on Zoom? I'm asking. Okay, so and those on WhatsApp, not WhatsApp, YouTube, that we are worried they can't hear me. Can you hear me now clearly? I'm waiting to have the signal from YouTube. YouTube, can you hear me all right? Okay. So, good morning, class. Welcome to our third and last lecture with me. Generally, this is the sixth lecture under this course. The first three we are taken by Dr. Ogude. The next three is being taken by me. And the other three will be taken by Dr. Lucky. So this will be my last one. And those that have been here since will go and rest a little. Okay, last week, the topic was on computer software and programming languages. Talk generally about what programs are, the set of instructions, telling the computer what to do and how to do it. We differentiated it from algorithm, which is simply a step-by-step set of instructions, step by step. And the algorithm together makes up our program. We looked at characteristics of what a good software should be. Stuff like usability, reliability, functionality, efficiency, and the rest. Then we divided computer software into two: system and application software. We first dealt with system software. After that, we now went to application software. Now, under system software, we are told what they are, mostly take care of the computer. And there are three types of them: the operating system, the utilities, and the language translators. And we dealt on each of them, one after the other. Then we came to applications. In fact, under translator, we looked at compilers, compilers, interpreters, and assemblers. Then we came to application software, applications, what they are. And under it, we looked at off-the-shelf software and, customized or tailor-made software. Under off-the-shelf, we looked at the general purpose software and special purpose software. And many of you are asking questions on the difference between the special purpose software under off-the-shelf software and customized, which was clearly treated. Then we came to the languages again, computer languages. We have low level, we have high level. Why low, why high? It was explained. I think that was where we ended last week. Am I correct, sir, class? So we should moving on to today's lecture, and I will share the slide now. Let me get it. Taufik Powers, you're raising your hand. I can't let anybody talk because of noisiness. It will be noisy. So if you have a question, and God help you, I see it on chat, I will answer. But remember, my eyes is not on chat, as your own eyes are there. I'm lecturing. So once a while, I might look there to check. But you can see now everybody's writing matric number, matric number. So what I will do now is I will disable chats. I will disable it. So whenever I want to ask, want to hear any question from you guys, I will enable it. And you can use that opportunity to ask your question. I think that should be better. All right. Okay, so let's fire on for today. The topic of today is information representation and number system, the language of the computer. That's actually what it means. So information representation is simply the different ways data, and knowledge can be organized, structured, displayed, so that computers and humans can understand and process them efficiently. The ways your data is represented so that computers and humans can understand it and process it efficiently. And of course, information representation involves encoding real-world concepts into a format that can be processed by machines and by humans. Ladies and gentlemen, there are different types of information, and since there are different types, each requires different ways of processing. And the different types can be what? Text, number, images, etc. So each of them require specific method of representing them. All right. Now, on your screen are the key aspects of information representation. I want to give us 10 seconds to look at what is written on the screen and we continue. 10 seconds. Oh yeah, now let's continue. Bits and bytes, binary representation, character encoding, numeric representation, etc. So, ladies and gentlemen, each of these aspects listed on your screen in how information is perceived, how information is processed, in how information is utilized across various fields. Data structures, database representation, those that will be will become to the tone level above. So have a look again on it. 30 seconds. All right. Data structures, database representation, graph representation, Boolean, machine code assembly language, semantic representation, and mathematical notation. So effective information representation plays a vital role in human-computer interaction. So the way information is represented in the system is very, very important on how you, the human, is able to interact with the computer. Because first and foremost, the two of you must speak the same language, thereby, enabling efficient communication and decision making. So let me go back to the previous slide, bits and bytes. So I've dedicated in fact, I think I dedicated a slide to each of them. So we'll speak on each of them slide by slide. So bits first and bytes. Okay. This is the slide for the bits and bytes. Sorry, this is my system shaking. Okay. A bit is the smallest unit in computing. A bit is the smallest unit. And it is you guys know, everybody know what is SI unit. SI unit of this, SI unit of that. SI unit of mass is kg, kilogram, right? Abroad, in US, I think it's pounds, but in UK and Commonwealth countries, it's kg. SI unit of time is second. SI unit of height, I think it should be meter. I guess so. So let me put it that way. The SI unit of measurement of data is bits. And a bit is the smallest unit. 1 bit is the smallest unit in computing. 1 bit represents a single binary value. Whereas a byte comprises 8 bits. So I repeat, a bit represents a single binary value, 1 or 0. Remember, the language of computer is only 0 and 1, nothing like 2, 3, 4. So the computer understands the binary system. So 1 bit, a single binary, could be 1, it could be 0. That's the smallest unit in computing. And a byte, B-Y-T-E, is on your screen. comprises 8 bits. So a bit can represent only 2 distinct values, 0 and 1. Whereas a byte can represent 256 combinations. It is pure mathematics, that's 2 raised to power 8. So a bit can represent only 2 distinct values, 0 and 1, while a byte can represent 256 combinations. And how did I get 256? It's 2 raised to power 8. Can combine. That's bits and bytes. So your takeaway here is that a bit is the smallest unit, and 8 of them make up a byte. So the screen shows us that a word is made up of how many bytes, how many bits is on the screen. We can count it straight away here. Even without counting, I can see 2 bytes. That means it's going to be what? 16 bits. We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So a word is made up of 16 bits or 2 bytes. When I say word, it doesn't mean like English language word. You spell book, house. No. It's in machine understanding. A word is made up of 16 bits. So if you see 16 bits, we call it a word. If you see 2 bytes, we call it a word too. Okay. The next one is binary representation. Each of them have a slide. I give us 10 seconds to read what is written there. Okay. We are told on the screen that the binary representation or the binary system is a way of representing data using combinations of zeros and ones. When I say data, it's not something in the cloud or something in heaven that's abstract. Data is what all you do every day with your system. The text you are reading, the image you are seeing, the audio music you are listening to, the video you are watching. These are all data. Ladies and gentlemen, that YouTube video you are watching can be represented using zeros and ones. You are seeing a video on YouTube or on your Instagram, but computer is only seeing zeros and ones. So binary system represents data using combinations of zeros and ones. I can pick someone's name, let's say Audu. And that Audu, A-U-D-U, can be converted into zeros and ones. For example, it could be 001, 0000111010. I'm just saying. And you'll be looking at your name and you don't understand this is the binary representation of your name. So binary representation, guys, is the foundation of how computers process and store information. Computers process and store information using zeros and ones only. And since computers operate using electrical signals, electrical signals can either be on or off. That is why all data, whether numbers or text or images or sounds or audios, must be converted into binary form. By the way, computer science originated from electrical engineering. And in some universities in US, for example, the faculties are still called Faculty of Electrical Engineering and Computer Science. In MIT, in US, it is called Computer Science and Electrical Engineering, something like that. So it's all computers came about because they operate using electrical signals. And signals can be on or off. On is 1, off is 0. So the 2 digits in binary. So since computers are operating using electrical signals, therefore all its data, whether they are numbers or images or whatever, must be converted into binary form. So ladies and gentlemen, binary representation refers to a method of representing data using only 2 digits, zeros and one. And these zeros and ones serve as the fundamental building block for all digital data in computers. Your laptop, your mobile phone, whether yeye phone or not, your digital devices, any smartphone, touch screen, internet TV, name them. Their foundation, they represent their data using only digits, zeros and one. So each zero or each one is called a bit, and combinations of bits represent numbers, letters, images, and other data types. All right, let me release the chat for just 1 minute. If there are questions, you ask. I did not even look at YouTube to know questions there. So once I'm doing the lecture, my whole screen is covered. For me to go view the YouTube, I will need to disengage my sharing on Zoom. Therefore, you guys can be helping me. If there are questions on YouTube, you can copy it there and paste it here on Zoom whenever it is released. So because students have refused to listen, I said, don't put your matric number, don't put your name, but they continue. So sometimes we are the architects of our problems. So I will have to disable charts again, because I can't open it and be seeing names matric, names matric, names matric. They are useless to me, and thereby missing some questions. And I will not come and be stressing myself and be going through to find questions. As you guys say, I can't come and kill myself, Abi. Okay, so about bits and bytes, let me go back. Someone asked question again. 0 is equal to a bit. 1 is equal to a bit. But if you combine them, you are now getting bytes. So 8 bits is equal to 1 byte. 8 bits is equal to 1 byte. Let me see whether I can write something here. So 1 byte. Let me just leave it at BY. I can't write out everything. I'm drawing using my bare hand. 1 byte is equal to 8 bits. One byte is equal to 8 bits. That means 2 bytes will be equal to 16 bits. 3 bytes, you should be able to tell what it is. And I'm saying that a bit is the smallest unit in computing. Nothing is less than a bit. A bit is 1 bit. And what is 1 bit? 0 or 1. So let me write a number beside here. 1, 0. Sorry, I'm drawing with hands though, so bear with me. 1, 0, 1. This is 3 bits. It's not up to a byte. Let me add something in front, 0. This is 4 bits. Let me add at the back, 1, 1. This is 6 bits. Let me add something here, 0, and something here, let's say 1. How many here? 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits, which is also equal to 1 byte. So that's the explanation. There's nothing much here. And I said that a bit can represent only 2 distinct values, 0 or 1. And a byte can represent 256 combinations. Do you understand what I mean by combination? See, this is one combination. This is a byte. There are 8 of them. You can change numbers, provided you make them 8. It could be 1, 1, 1, 1, 8 times 2. It could be 0, 0, 0, 0, 0. It could be 0, 0, 0, 0, 1, 1, 1, 1, So the combinations, eight digits, each, 8 bits, you are going to get 256 combinations. That's what I mean. If it was only 2 digits, let's say 1, 0. How many combinations are we going to get? Let's see. The first one is 1, 0. It could be 1, 1. It could be 0, 0. It could be what else? 0, 1. Is there any other combination? No. Check. There is no other combination you can get from here. I've listed all of them, 4. And the formula is what? 2 raised to power. How many digits are we dealing with? 1, 0. 2. Sorry. I forgot my mouse, so bear with me. 2 raised to power 2. Wait. Let me write it well. Well, power 2, Sha. You know what I want to write. 2 raised to power 2. How did I get this power 2? Because I'm dealing with 2 digits. Now, let me come under the screen and change the color. So let me say we are dealing with 3 digits. 1, 0. So, no, just 3 digits. Call it anything. It can be 110 or 001 or 000. Just 3 digits. How many combinations are you going to get with 3 digits? It will be 2 raised to power that 3 digits. So if you are dealing with 3 digits, you are going to get 8 combinations. You can try them. And finally, 8 digits, which is a byte. That was why I started. 8 digits, which is a byte. How many combination will you get? 2 raised to power 8, which will give you 256 combinations. So the first one, I can say, share 8 digits. I can say 11111 into 8. Next one, 111 4 times, then 000 to make it 8. The third one could be 0, then the rest is 1. The next one will be 2 zeros, then the rest are 1s. The next one could be 3 zeros, the rest are 1, etc. You are going to get 256. That is what I am saying. Okay. So we've talked about binary representation. We move to character encoding. The next slide should be character encoding, which is very, very important. Very, very. Now, character encoding, I know the screen is tiny, so but don't bother much. I will explain it. Character encoding is a system, that assigns a unique number to each character in a set. Let's say A, B, C, D to Z, English alphabet. A has its character number, has its code. B has its code. C has its code. Capital A and small letter a have different codes. So character encoding is simply a system that assigns a unique numeric value to each character in a set, therefore allowing text to be stored and transmitted electronically. So it determines how characters are represented in binary form on computers. And there are 2 character encoding we have written on your screen. The ASCII, American Standard Code for Information Interchange, and the UTF-8, that's Unicode Transformation Format. Well, if you want, you can cram these names. This is character encoding methods used by the system, used by your digital devices to convert characters, to convert symbols into numbers, and those numbers are now converted into binary. And we are going to delve into that, but I will have to be fast. How I wish I had my mouse. I don't have it, so something that I will write, I will say them. For example, if we look at the screen, I know you are stressing your eyes, but just bear with me. Let's say ant, the word ant, ant that crawls on the floor, A-N-T. Let me write it on top, A, then small letter N, small letter T. How will this be read by the system? First, character encoding will come into play. After that, that number is converted to binary. So before conversion to binary, let's even see how this word is converted to number using the table. So the table we are seeing on our screen is the ASCII code, the number one here. Look at where I'm hovering my mouse. This is the ASCII code. The table you are seeing on your left is ASCII. Now, capital A is, I can't even see this thing very clearly, 065. So below your screen, I'm writing them down now. For A, let me use red, will be 065. That's capital A. Small letter N will be 110, 110. And small letter T would be very small letter T. I've forgotten how to read ABCD. 116, 116. This word ant has been converted into this numeric value. Then this numeric value is converted into binary. I don't want to rush us into binary system now. However, I want to throw a challenge to you guys that you must have done conversion of binary number to numbers to binary and binary to numbers. If you have not done it, I think that should be done. Let me think when. I think it should be done by me. How a number is converted to binary. For example, I ask you convert 6 to binary number, convert 7 to binary number, convert 500 to binary number. We should be able to know that. So I'll move fast, reach there, we convert. So here you see ANT has been converted to 065110116. However, this number you are seeing here is not a binary number. Binaries should only be ones and zeros. So this number is then converted to a binary number using the binary system so that the computer will understand what is written, so that the computer will interpret that, this is ant written. Okay. Next slide. And numbers can be represented using various numeral systems. There are many of them. The one we are interested in is the binary number, but you have the decimal, base 10. You have the octal, base 8. You have the hexadecimal. So each are different and are used for different applications. But for machines, for computers, for digital devices, it is the binary system, base 2. So numeric representation refers to expressing information or your data using numbers instead of words or other forms. So it's a way of quantifying or symbolizing things to make them easier to process, easier to analyze, easier to compare by the machine, by the computer. So that's what I mean by numeric representation. We'll come to practical stuff. So these are just those factors that play a big role in information processing. Text representation, the previous one was numeric, that's numbers. This one now is text. It refers to expressing data or ideas using written or spoken words, sentences and symbols, as opposed to using numbers or visual forms. So it is the way information is conveyed in a readable, understandable format using language. And essentially, text representation makes complex data or abstract ideas more accessible, offering clarity, meaning, and the rest. There are some ideas that if you represent them in the form of a text, it becomes clearer. Complex data becomes more meaningful when they are written down in form of a text. So these are all information representation. Okay, the next should be image. representation. So you know already what is image. It involves expressing your data. Sorry, my system is just running crazy. Image representation is all about expressing your data or concepts using visual elements, such as pictures, graphics, diagrams, or any other visual media. And this representation translates information into a format that can be interpreted through visual perception rather than through text or numbers. So you don't need to read the text, you don't need to study numbers, but looking at the image or visual representation, you're able to perceive what is there. The next is audio. Audio involves conveying data, concepts, ideas through sound. Sound, that's the key word. It utilizes spoken language, music, sound effects, or any other auditory stimuli, to communicate information. That's about audio. The next is video representation. It involves conveying your, again, data, concepts, ideas. That's the three words I've been using. Conveying data, concepts, ideas, using moving images and sound. So it combines both visual and auditory elements, creating what I would call a dynamic and immersive way to communicate information. So, and video is often used when the information is complex, time-based, or when both sight and sound together can offer a clear understanding. And remember, for those that might not know, video is what? Moving images. You are moving images. Images are moving, and it creates that visual, video effect. Right? Then the data structures, these are slides. Let me take us for a moment back to where we started so that you'll understand what's happening. We started here, the key aspects of information representation. And I started by saying that when we talk about information representation, we are talking about how the computer processes, stores, manipulates information. And the computer here, I mean anything digital, your laptop, your phones, that traffic lights on the streets. These are all digital devices. So, and I mentioned and I listed aspects, key aspects of information representation. This slide went to the next slide. So I've dedicated one slide to each of them. So that's what we are looking at generally. So now we are now on data structures. So let me go back to data structures. And I said data structures and the rest of the slides now will be met many times by computer science department students. Mathematics students will meet data structures in 200 level. Computer science will meet it 200, 400, and okay. You guys now, computer science used to be 5 years, it's now 4 years. So you are meeting it 200, 300, and 400. Unlike before where you will meet it 200, 400, and 500. So data structures, what are they? They are ways of organizing and storing data so that it can be accessed and modified efficiently. And they provide a systematic way to manage and process data for various applications, ensuring that your operations are smooth, like searching, like inserting, like updating, like deleting. You have your database, you want to search for a particular entry, or you want to delete, or you want to insert, or you want to update. Data structures makes it easy for you to do. And on your screen are types of data structures, which we are not going to delve into. You have your arrays, you have your linked list, you have your trees, you have your graphs, etc. We are not delving into that, but it's good at least you know some types of data structures. What are arrays? What are linked lists? What are trees? What are graphs? These are food that computer science students will be fed with from 200 level. What they are, how they operate, etc. But at this stage, 100 level for everybody, what you should take away from this slide is that data structures are ways of organizing and storing data inside the computer memory. Why? So that you and computer can easily retrieve what you stored, You can easily search what you stored. You can easily insert more entries into what you stored. You can easily delete. You can easily update. Without data structures, it could be hard to, do some of these operations. Let me quickly diverse your idea a little bit. Let me draw a tree. A tree data structure can be like this. All right. Let me leave it this way. This is X. Now, you don't have much background knowledge of tree, but I will just, in a layman's way, explain. I want to search for X. There are three things I stored in the memory. T, A, and X. They are the three things I stored in the memory. This T can be an image, can be a text, can be video I stored in my computer memory. X can be anything. Can be text, can be audio. It can be diagram I drew. E can be anything. So there are three things I stored in the memory. And by the principles of three, for you to access anything, you must pass through the head, T, before you go deep. There can be other things. So let me draw. There can be very much other things stored. But the search must start from T. Now, ladies and gentlemen, if I want to access X, I want to see X, see what is there. Maybe I want to delete it, or maybe I want to add something there, or whatever, or I want to update it. I must start from T. So from T to X is one step. From T, I move to X. It's just one step. Very fast, right? When I look at linked list, linked list is a linear data structure. Let me call it a straight line, but really, it is not. Well, that's how it is represented. How many do we have here? 1, 2, 3, 4, 5. This is also stored in the memory. Right? Stored in the memory. This is T. Right? All right. And this could be X. What's happened now? Okay, sorry. This is X. Wait, so 1 minute. I think my pen disappeared. That's what is happening. Okay, this is X. This is A and the rest. Now, if I want to access X, one step from T, fine. But if I want to access A, it's 2 steps. 1, 2, it takes time. But if you look at the tree here, if I want to access A, it's 1 step. I'm just explaining this in the layman's way. Data structures, what they help to do, they quicken our operations, depending on the kind of operation you are doing. Trees are known to be faster than linked lists, but linked lists also have the advantages. So your job is not to go and study tree. Your job is not to go and study linked lists. Your job is to know that data structures are ways of organizing and storing data, so that data stored can be accessed and modified efficiently, faster. That's all. That's what you need to know here. Okay, so we move to the next. Database. We all know about database, where you store something. It refers to the way data is structured, stored, and organized within your database system. Again, not just how it is stored, structured, organized, but such that what is stored can be efficiently retrieved, can be efficiently managed, can be efficiently manipulated. So if your database is well designed, well organized, then whatever is stored there can easily be accessed. I want to look for a student whose matric number is so. If I type that matric number in my system, it will bring out that student. Unlike when I will have to start searching from student number 1 to that student, it will take me much time. So the way the database is designed, the way it is structured, the way it stores data determines how fast, how efficient you'll be able to manipulate your data stored inside it. The next is graph representation. Graph is a way of structuring and organizing data using graph theory. Where data entities are represented as nodes, and the relationship between those entities are represented as edges. I can draw a graph here to show. Let me draw it. A graph looks like a tree, but it has a loop. This is a graph. And I can also draw like this. This is a graph. And it can represent anything. I'll give an example of what it could be. C, D. Now, A could be, I'm just giving you an example, a very layman's example. So the straight lines represent relationship. So this straight line I crossed here, it represents the relationship between A and B. A and B could be anything, it could be states. For example, A could be milk. The straight line could be Milo. B could be tea. So that means A with Milo will give you tea. That's milk with milk. Abi, I don't know chemistry much. A could be water. And the straight line relationship, water plus what will give you something. So I'm trying to get that. So B can be the end product. A could be water, whatever water is mixed with, it gives you B. It's a relationship. Or the straight line could be heat. Now, cold water added with heat will give you hot water. Something like that. So graph is used to represent relationship between entities. So the node A, B, C, D represent the entities. The nodes, or they are called vertices. While the edges, the straight lines, represent the link. The relationship between those two nodes is linking. So that means there is a relationship in this diagram. There is a relationship between A and C. There is a relationship between A and D. There is no relationship between B and D. But if I add something here now, I can now say there is a relationship between D and C. So this graph representation. Okay. The next, Boolean algebra. It's simple. It's a branch of mathematics that deals with variables that can have one of two possible values. So it's a branch dealing with variables that can be true or false. You know, no other thing. So variables that can only take two values. And the values could be true or false, 0 or 1 or 0. Now, like your switch in the house, it can take two values. One up, that's what do you call it, off or on. So if you take it up, light goes off. If you take it down, light comes on. So two values. And it is used for manipulating logical statements using operations like and, or. So your takeaway from this screen is that Boolean algebra deals that can have two possible values, true, false. And true is typically represented using 1, and false is typically represented using 0. Okay, I think I'm done with that list. Let's go back and be sure that we are done with it. Let's go back. Okay, remaining three, machine code and assembly language. We've been hearing about it since. Machine code is the lowest level programming language. Said that. And it has zeros and ones. That's the symbols. It has zeros and ones. And these zeros and ones is what the computer CPU can directly understand, execute. Your central processing unit of the computer can only understand zeros and ones only. It is the only language that is directly understood by the computer hardware without needing any translation. So it is represented via machine code. So machine code instructions are represented in zeros and ones in binary system. And each instruction corresponds to a specific operation, like adding numbers, moving data, jumping to different parts of the program. While assembly language is a human-readable representation also of machine code, but it uses mnemonics. I've said this before. Mnemonics like symbols, signs, short words. It uses them to represent the binary instructions that the CPU understands. So yes, assembly language is a low-level language. It is still far easier to read and write compared to zeros and one, compared to the machine code, gum. All right. Then second to the last slide for our first part, semantic representation of information. It refers to how the meaning of data is captured and structured. The meaning, how it is captured and how it is structured so that it can be understood, processed, interpreted by both you and the machine, by the computer. So unlike syntactic representation, which focuses on the structure and form of data, semantic deals with the meaning behind that data, ensuring that the relationships, the context, the intent are preserved and accurate. That's all right. Then mathematical notation, which is the last, is a system of symbols used to represent your mathematical concepts, your operations, your relations, numbers, etc. Mathematics, allowing for concise and accurate expression of complex ideas and formulas. For example, A is equal to 2 times B. It means you have to bring 2 of B's to get A. That's what that is telling us. A divided by 2 is equal to 4. That means A will be equal to 8. For those that know maths, A divided by 2 is equal to 4. That means A will be 8. You see? So we are using notations to represent meanings and relationships. All right. I will release the chat for just 30 seconds. Get your question ready, if you have, before we move on to the second part of today's lecture. So let me release. And please do me a favor with those on... In fact, I'm not taking any questions from Zoom. Let me take questions from YouTube. Let me take questions from YouTube. So I'll have to use my phone to quickly connect to YouTube so that, let me get the link. I sent it to the group here so that I can see questions coming up there. Let me take questions from YouTube. So I'll use my phone to quickly connect it to YouTube. And with you, let me mute it here. Yes, I will be echoing myself here. You get the link. I sent it to the group here so that I can see questions coming on there. I don't know why I can't. Okay. So let me mute it here. All right. So let me see the questions. I'm not seeing question. Okay, question I see here. Do we have to know the RC code? No, you don't have to cram it. However, if you are given a sample of it, will you be able to convert some words? I think it's the simplest thing to do on it. If you are given a sample of the RC code, will you be able to convert it? So, yeah. Is assembly language a high-level language? No, assembly language is a low-level language because it uses symbols, signs, and some words. And those symbol signs are still very far from human understanding. So it is a low-level language. I will not read everything, so I don't really get assembly language. Assembly language, now, what are you not getting? Assembly language, I said, is a low-level language, and it comes in the form of symbols. Assembly language used to be popular before, but nowadays it is no more in existence. Unlike normal programming languages where you write some code, some short abbreviation, assembly language uses signs and symbols to represent whatever data it is communicating to the machine. It is a low level because the signs and symbols are very far from human understanding. You will not see signs and symbols and understand what is being communicated. Therefore, that's why it is a low level language. I hope that is clear. So it is a low level. There are two low-level languages, assembly language and the machine code. Machine code is worse because it is only zeros and ones. And we cannot, if you see your name is zeros and ones, you will not be able to interpret it until you sit down and start converting it back to English language. But assembly language, yes, some symbols, you can see a symbol and guess what it is talking about. However, it is still a low-level language, not a high-level language. What is the difference between low-level and high-level language? I will not answer that question because this is a lecture we did last week. So please find the video, take the slide, read it, you will get the answer to that. Yes, humans made someone said, but humans made the signs and symbols. Human made the signs and symbols. It is one thing having a sign. It is another thing combining them together. Don't you know what is zero? Don't you know what is one? Is it not human that invented 0 and 1? But if I convert your name now, Mayo, if I convert your name to zeros and 1, will you understand? You will not understand. Then I will ask you, are you not the one that did zeros and 1? Why are you not understanding it? We are combining them now to form something else. So it's not that easy to see and understand. That is why assembly language is a low-level language. Okay. Another question here on Boolean algebra. I say Boolean algebra is a branch of mathematics that deals with variables that can have one or two possible values. Any variable that can take just two values, then we are talking about Boolean variable. For example, a coin. A coin can take only two values, either the face or the tail. So you can call the face 1. You can call the tail 0. I mean, when you want to represent face and tail in the system, in your computer, you're not going to write face or tail. You can call 1 or 0. So, and all these, I'm not asking to go deep, but to know surface, what is it? So, Boolean algebra. Algebra is a branch of mathematics. So, Boolean is that branch that deals with variables that can have one of two possible values. I use switch for you to. Switch can be on and off. Switch can't be on and off at the same time. So yeah, but you can read more on that, please. Then is machine code a low-level language? Yes. There are two low-level languages, machine code and assembly language. They are the only two low-level languages. Why low? It was explained in last lecture. So take the video of last lecture and read why they are called low. The high-level languages are all other languages that you know, programming languages. Your Python, your C++, your C#, your Java, etc. You said I didn't explain the database representation. I explained it now. How? How didn't I know? How didn't I not explain it? I explained it. That this database representation of information refers to a way data is structured, a way data is stored, a way data is organized within a database system so that it can be easily or efficiently retrieved, managed, manipulated. And I remember using matric number as an example. Now, if I want to search for a matric number of a student in the Premier platform, we have a system, a database. Once you type the matric number, it will bring out the students. Why is it so fast? Because the way all matric numbers we are stored in our database is efficient. So that's why out of like 30,000 students, we are able to, within seconds, retrieve the records of one student. Had it been that the database is poorly structured and data there is stored anyhow, it will be hard. It will take time for the CPU to read through the database to find whatever entry we are looking for. Okay, I will take last question and we'll move on. I can't take everything. And I've told you that you can always send your questions through your COS representatives. They will write the question down for me and I will explain. Okay. Another question, what is the difference between low-level language? So the difference between low-level language and high-level language is in our lecture, previous lecture. Get the video, read it, listen to it, and take the slide, look at it, especially the video. It was well explained there. So can we say traffic symbols are example of? No. There are special symbols. Or now, after this lecture, do yourself something. Type assembly language. Just write brief explanation of what assembly language is. You will see. Assembly language has its own special symbols and characters. Not any symbol you come across. No, it has its special symbols, its special signs, and its special word it uses. It's not any symbol. It's a programming language. For example, in C++, if you want to declare an integer, you write int. Oh yeah, now check in assembly language, if you want to declare an integer, what is it? So it uses its special symbols and signs, its own. All right, so I will stop now so that I will move on with my lecture, even the harder parts. Okay, thank you very much, YouTube people. So now we are coming into the main thing. We never even enter, you're already shaking. The number system. The number system. Computer number system. So computer number system, ladies and gentlemen, is a way, we've said it already, representing numbers in a format that computers can understand and process. And I've said already before that since computers operate using electrical signals, they primarily use the binary number system. And the binary number system is zeros and ones. 0 and 1. However, for human understanding and convenience, other number systems are also used in computing. For me and you to be faster in understanding our data, we use other number systems like the decimal number system. That is the popular one human beings use. We count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the decimal number system. So it is for convenience and for easy understanding by human that we use other number systems. You have the octal number system, you have the hexadecimal number system. Hexadecimal number system. You have the decimal number system that we use. I think the next slide gives us some examples of them. Yeah. So the decimal number system is the most popular. That's base 10, and that's what you and I use in our everyday life because the digits used are 0 to 9. Example, any number you can call 456, 300, 19, 12, 49. These are all decimal numbers. And it is used in our everyday human calculations. But you have the binary number system, which is used by the machine. You have the octal number system, you have the hexadecimal number system, and also other number systems. Our next slide will just give us examples of the others that I listed here on the screen. So the next slide that I'm going to touch now will show us example of octal number system, characteristics of it, that of hexadecimal, of course, that of binary. So it is on our screen, and you remember you get this slide. I wouldn't want in Dr. Lucky's class, you'll be asking Dr. Lucky, sir, what is binary number system? We will refer you to this lecture. So that's why you should always be in a class. Let me give you one secret. That you are getting the video after lecture doesn't guarantee that you will watch it because, ladies and gentlemen, you will not have the time. I've been in the system for a while, so I understand and I know this. You will not have the time. Do you think you have the time to spend 2 hours on each lecture when your exam is like 2 weeks to go? You will not have the time because you have other lectures too to attend to, as in to listen and study for the exams. So it will be unfortunate if you are not in the class here and you are waiting for this video. Which time will you have to listen to them? Unless, of course, there are very good students that after lecture in the evening, they go through their recorded videos. But then it's 2 hours now. Will you have that time? So it's better you listen to it now and then maybe you can now look at the video, specific points in the video to understand more what the lecturer said there. So on your screen are the 4 types of number systems that I talked about and their characteristics. So the digits used are shown. So I want to concentrate on the second one, the binary number system, base 2. It uses zeros and one only. Example is given, and used in computer, digital electronics, machine, and it's a machine language. You have the octal number, there's a decimal. So the assignment I will give you here is just go and study. Just know the numbers used for them. Like for octal number, know that it's from 0 to 7. Oct means 7. Then the hexadecimal, what number? 0 to 9 and A to F. You can know this. And see the example, how they look like. Example of octal. Example of a decimal system that we use. Decimal, we say 10. We don't say 10 base 10. We don't say 2 base 10. Actually, that's what it is, 2 base 10. 500 base 10. The numbers you and I use every day is base 10. But we don't call base 10 because it's assumed that we know that we are dealing with decimal number. Okay, so we are now going into mathematics a little. Anyway, I stop, we take it that way. We are to convert decimal to binary and also binary to decimal. So this thing written on the screen, I'm not going to read it. It is a slide, take it and read it. However, I'm going to straight go into what is written on the screen. Go into the mathematics part of it. It's been a while I taught this decimal, so I hope I will not make mistake and Manchester United people will start laughing at me. So the next slide, let me repeat what I just said now. What is written on the screen is how to convert a number to another system. That's convert a decimal number to binary and how to convert a binary to decimal. Why items here? 4 items are, listen carefully. 1 is how to convert your normal decimal number to binary. 2, how to convert your normal decimal number, but a fraction, not just the whole number, fraction to decimal, to binary. So I've mentioned 2, remaining 2. Let me repeat the 2 I've mentioned. How to convert whole number decimal to binary and how to convert fraction number decimal to binary. These are the 2. The other 2 is the opposite. How to convert binary to decimal and how to convert fraction binary to decimal. There are 4, and these are the 4 that is written here on your screen. So the next slide is this. It's your take home, because I'm going to deal with binary since computers deal with binary. Learn, ladies and gentlemen, how to convert your normal number decimal to octal number system. And back, how to convert octal to decimal. This is your take home. You are not submitting it, but you must learn this. The other one is how to convert your normal decimal numbers to hexadecimal number system and back. We have to learn this. Now, I will be opening a whiteboard, but I don't know whether I will be able to deal with the number because as you are touching the screen, you'll be shifting my hand. So if my hand is shifted, I will just close it and come back to this slide and draw whatever I want to draw here. So give me a minute. Let me open a whiteboard. Not blackboard again, whiteboard. Where is my whiteboard? A minute. Yes, I've seen it. So you'll be faster than me because you are writing with your pen. So there are 4 things I want to do, and I want to do it fast. To convert a decimal number to binary, 1. 2, to convert fraction of decimal to binary, that's 2. 3rd, the opposite, to convert whole number binary to decimal. And 4th, to convert fraction of binary to decimal. So we are converting decimal D to, I don't know why this thing is shaking today, my screen, to binary. Wait. To B. And also binary We are converting to decimal. Now, let me convert. Let's start one. Let's take any number for now. Let me take 7. You guys know this. You did it in secondary school. If you didn't do it in secondary school, then you don't used to attend class. Simple as that. I want to convert 7 to binary. So I do it this way. Easiest way, 2. So you'll be dividing. That's what that text I say you should read is saying. You'll be dividing it by 2 until you have 0 as, remainder. Now, 7 divided by 2 is 3. Remainder 1. I would have been changing the color, but remainder 1. Let me just leave it that way, Jerry. 3. You put 2 again. 3 divided by 2 is 1. The 1. You put 2 again. 1 divided by 2, you will not get any whole number. So 0. Remainder 1. So 7 converted to binary will give you from up down. Or is it from down up? Remind me. Okay. It's from down up. All of them are the same. That's why I need to tell you how we are picking it. So it will be 1, 1, 1, 1. So 7 converted to binary will give you 1, 1, 1. From down up, I picked my 1, 1, 1 because I know all of them are 1, 1, 1. So you'll be confused from where are we picking. I will do another example. So normally we write that 7 is 10. Is equal to 1, 1, 1 base 2. So if you see base 2, you know that we are talking about binary. The next, let me pick another number. Okay, can someone on YouTube pick a 2-digit number for me? The first person I see on YouTube, I will pick the number. A 2-digit number. But let's convert it to binary. And that will be the last two. So watch. I will not do 3 examples. 2 examples is enough. 37. Okay. So let me check 37. So we can change color. So this one is ended. 37. We are converting it to binary. It's your rehearsal I'm doing for many of you ogas and madams here. I'm wasting my time. You know it already. 2. 37 is to be converted to binary. So you start dividing by 2 till further notice. I hope you understand what I mean till further notice. 37 divided by 2 will be how many? Oh, you can't talk, right? All right, that will be 18, I guess. Abi? Yes. Remainder 1. 18 divided by 2. That will be 9. Remainder 0. 9 divided by 2. That will be 4. Remainder 1. 4 divided by 2. That will be 2. Remainder 1. 2 divided by 2. That will be 1. Remainder 0. And finally, 1 divided by 2, it will not go. So 0, we end when it is 0. Remainder 1. You are picking it from down up. So let me come a little bit on your left to write it out. So 37 converted to binary will be 1, 0, 1, 1, 0, 1. Is the binary equivalent of 37. Those on YouTube, am I correct? Am I correct, or is there a place I made a mistake? Even if I make a mistake, you know the procedure now. You know what to do. Just be dividing by 2 until you have 0 at the end, and that's all. So I believe we are correct. All right. This you might meet. You can imagine if you are asked to do this within 10 seconds. Nobody is telling you to do this within 10 seconds. But the exam now, the total duration of the exam might just be 30 minutes to answer how many questions. So some of these things should be very, very fast. So as far as I'm concerned, I've done conversion from decimal to binary. Now, I will now also do another conversion, but this time a fraction. A fraction. How to convert, fraction from decimal to binary. So let me clear my screen. How do I clear it? I'm coming. Okay, maybe this. Yeah, I've cleared it. Okay, I'm reading what YouTube is saying, that there was a mistake in division. All right. I've cleared the screen, but at least for you to point out the mistake, that means indeed you know and you are following. So I'm being told that when I divided 4 by 2, the remainder should be 0, not 1. So, but what is to be done, that's what matters most. You'll be dividing the number. If it cannot be divided by 2, remainder must be 1. If it is divided by 2 totally, the remainder is 0. After you finish dividing and the last number you're having is 0, then you pick your remainders from down up. Thank you for pointing that out. Thank you very much. Now, let me pick another number, also decimal, and let me say 0, a simple one, 0.0 2. It's a decimal number to be converted to binary. What do we do? Can someone quickly type? To tell us what to do. On YouTube, I'm waiting. Sorry, Zoom, YouTube people today. Type, let me read and see what we can do. If this is what you guys know, I wouldn't be too fast in that. This is a decimal number to be converted to binary. So it is not a binary. Well, seen today will tell you it's not a binary number. So we are converting a decimal fraction. YouTube. Whether what you guys are saying. Okay. Use negative powers. You made a mistake. Yes, now here that I made a mistake and I've corrected it. You are not converting anything to whole number. How do you convert fraction to whole number? Can you convert half orange to full orange? No. I'm reading what you guys are writing. I've written a fraction as 0.02. How do we convert this to binary? How do we convert it to binary? Okay, let me see what we can do. Maybe you guys might have your ways of doing it. So let me see. Now, we are multiplying it by 2. Abi? Yes, we'll be multiplying it by 2 until what we have at the end, the fraction side is 0, 0, 0. If I'm correct, so let me check. All right, let's start. Watch what I'm doing. I'll be explaining it, Sha. 2. So wait, let me use an easier number so that I can explain it quickly. Let me write 0.05. So pardon me, you will see reason why I'm using 0.05 so that it will end quickly. That's just the reason. So if a question is to be brought for you in the exam, of course, you will not be given a number that will take you 20 years to finish. You will give a number that should finish quickly. What matters is not how long, but what is the process? Do you understand the process? That's what really matters. Okay, so you multiply by 2. So this number is to be converted to binary. So we start multiplying by 2. 2 times 5, 10. Watch me. Carry 1. 2 times 0, 0 plus 1, 1. Sure, I'm correct. Well, let me be moving. So see what I did. 2 times 5, 10. 0, carry 1. 2 times 0, 0 plus 1, 1. 0. No, no, I want to get a number. You might not understand what I'm searching for. Sorry for the confusion. I want to get a number that will make things 0.25 should go. Yeah. My apologies, please. My very big apology. I'm sorry. I'm sorry. You will see reason. You will understand why, what I'm saying. We have to convert 0.25 to binary. And the 0.25 is a decimal number and it is a fraction, right? So let me start multiplying by 2. You will see why I was choosing one that will end quickly, not infinite one. 2 times 5, 10, carry 1. 2 times 2, 4 plus 1, 5 points. 2 times 0 is always 0. So let me use blue to mark this 0. After that, keep this 0 that I underlined. And you continue with your multiplication again. 2. 2 times 0, 0. 2 times 5, 10. Carry 1. 2 times 0, 0. Then 1 comes here. So we keep this and we stop when the fraction side is 0, 0. You see, that's why I chose a number that will end quickly because of lecture. When the fraction side is 0, 0, you stop. Now you pick your digits from up, down. Remember when we are converting the whole number, we picked from down up. But this one, you pick from up, down. It is a fraction, right? So it is going to be 0 point whatever you want to do. You now do it because it's a fraction that we converted. So it's going to be 0 point. I've not picked anything yet. Then you pick from up, down. That will be 0, 1. That's the fraction conversion of this number, 0, 1. Let me see the work going on in YouTube, whether, okay. Okay, you see, a Chelsea fan can solve mathematics correctly. Not always yabbing us that Chelsea fans are mostly motopark aberos. We are not aberos, mind your mouth. So I can use another number. So I'm trying to use a number that will make me finish quickly. Complete the multiplication quickly. When do you stop? You stop when the fractional side is 0. You stop and you pick your numbers from the first, whole number. Here could be 1. And this is where I started picking X. I did not start where Y is. I started at X. However, since it was a fraction, so whether you like, you have to write 0 points, then you pick your numbers. This is converting from a decimal fraction to binary. So this our binary 0.01 is the binary equivalent. So there could be other examples. So, but before I move out to this, I'll give you an example and leave it for you to go and solve. Remember, we converted 37, right? All right. I want everyone to learn how to, I will explain how to do it, but I will not do it. 37 point 25. Remember, we did 37 initially. Now we did 25. It's 0.25. How is this decimal number converted to binary? So listen if you don't know, because I know most of you already know. You convert 37 using the method we used. You get your answer. Let's say the answer is X. You convert 0.25 using this method we use on the left. We get the answer. Let's say it's Y. You now add two of them together. Let me check YouTube to know what we got under 37. If I can get there, so many messages there. Let me explain so that you will see. Or can someone quickly write it down again on YouTube? What we got when we converted 37. There are so many messages to browse through here. Write me again on YouTube what we got when we converted 37. When we converted 37. Okay, 100, 101. So when we converted 37, we got 1, 0, 0, 1, 0, 1. 1, 0, 1. Now, 0.25, we got 0.01. See it here. See how I'm adding. 0 under it. 0.01. So we are adding. So that's what I said. 37, you convert 37, it's a whole number. You get X. 0.25, you convert it, you get Y. You now add X and Y. X and Y, these are the two we are adding now. It's a straightforward addition. 1, 0, 0, 1, 0, 1, 0.01. This is equal to our 37.25. I hope things are clear. If they are not clear, it must be clear. Okay. Okay, let's do one. Someone ask one more example. So I'm clearing this screen. I'm clearing it, but I have to get a number that will go. I think I get one now. 0.125. You multiply by, so we have to convert this decimal number to binary. We start multiplying by 2. 5 times 2, 10. Carry 1. 2 times 2, 4 plus 1, 5. 2 times 1, 2. Points. 2 times 0 is 0. So we are keeping this 0. The whole number part, that's what we are keeping. And we continue to multiply by 2. 2. Again, we multiply. 2 times 0, 0. 2 times 5, 10. Carry 1. 2 times 2, 4 plus 1, 5. Points. Nothing here now, 0. We keep this whole number. And we continue with our multiplication. 2 again. 2 times 0, 0. 2 times 0, 0. 2 times 5, 10. Carry 1. 1 is here. So we stop when the fraction sign is 0. And you pick your numbers from up, down. So is it a fraction? Yes, it's a fraction. So big 0 point, we pick our numbers, 0, 0, 1. So this is the binary equivalent of 0.125. I think we should now move on. All right. Now we are coming to, it's been a while I did this, so it makes me become a student again. Okay, before I clearly look at it very well. Now we are done doing decimal to binary. We are now to do binary to decimal. So let me bring out one binary number. I will leave what is written here. Let me take this space under and do whatever I want to do. So let's use green. A binary number, let's say 1, 1. In binary, you don't call it 11. These are digits, 1, 1. This is a binary number, so be careful with the questions. Either the word you hear binary, or you hear under it, you see under it here, 2. That means it's a binary number. So we have to convert this binary number to decimal. So don't come and say, so how do we know whether it's binary or already a decimal? Because you have 11 too in our decimal number system. But you have been told that this is a binary number. So use the powers to multiply. And I'm not here to teach powers. So this is 2. Let me use a color. The easiest is binary to decimal actually, because both fraction or whole number is almost the same. This is 2 raised to power 0. Here is 2 raised to power 1, etc. If there was other numbers here, it would be 2 raised to power 2, 2 raised to power 3, etc. So what do we do? Green times red plus green times red, etc. So let's start from the leftmost. 1 times 2 raised to power 1, right? Plus big plus. Remember your board mass. Another 1 times 2 raised to power 0. So we are getting 2 raised to power 1 is 2. 2 times 1 is 2. Plus 2 raised to power 0 is 1. 1 times 1 is 1. Remember, any number raised to power 0 is 1. 200 million raised to power 0 is 1. 5 raised to power 0 is 1. 419 raised to power 0 is 1. So that's how I got this one. So this is equal to 3. Well, base 10. Or you call it 3. So 1, 1, a binary number converted to decimal number will give you 3. Now, those on YouTube, can you give me a number in binary? Let's try. A number in binary, let's try. A number in binary, let's try. One more example, that's all. Whole number, not fraction, please. The first that appears on my screen is the one. 56 is a decimal number. Mr. Man, I say binary number, you're writing 56, writing 4. How I wish there is Ken, we start flogging some people. 1001. That's the first one I saw there. 1001. 1001. 1001. So 1001. It could be longer. It could be longer. All right. Now, start placing your powers 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, and 2 raised to power 3. So what we are doing is red times purple plus red times purple plus red times purple plus red times purple. So let's start from the left. 1 times 2 raised to power 3 plus 0 times 2 raised to power 2 plus 0 times 2 raised to power 1, and finally plus 1 times 2 raised to power 0. So 1 times 2 raised to power 3, 2 raised to power 3 is 8. 8 times 1 is 8. Plus 0 times anything is 0, so we don't even need to bother. Plus 0 times 0, anything 0 times is 0. Plus 2 raised to power 0 is 1. 1 times 1, 1. So we get 9 as our answer. 9. So 9 is our answer. So 1001 converted to binary will give us 9. In base 10, that's in binary. Okay, I'm done with this. Now let's look at binary fraction. Binary fraction. Please note this answer. 1001, we got 9. Well, I think I remember it. I want to use it for something. So I'm cleaning this. Now, let me choose by myself. Then I will ask you to choose one. Binary number 0.101. Convert this to decimal. Sometimes nobody will tell you it is fraction. Are you not seeing points there? 0 point. That means it's fraction. I will not come and be telling you, hey, Oga, it is a fraction. Just the question might be convert the following binary number into decimal. So now, ladies and gentlemen, our 2 raised powers. Remember here used to be our 2 raised to power 0. Remember, here used to be our 2 raised to power 0. So anything after the decimal point will be -1, -2, -3, etc. So here will be 2 raised to power -1, 2 raised to power -2, and 2 raised to power -3. Yeah, you do your multiplication as before. Green times red plus green times red plus green times red. Just like before. All right, so well, let me write it down. If I just say let's go like that, some will still say they did not understand. Okay, so this will be, we are starting from here. From here, I'm pointing at. Okay, so to be 1 times 2 raised to power -1 plus 0 times 2 raised to power -2 plus 1 times 2 raised to power -3. Okay, so we now multiply out. Now, 2 raised to power -1. A number, let me use another example. 50 raised to power -1 means 1 over 50. 1 million raised to power -1 means 1 over 1 million. 7 raised to power -1 means 1 over 7. So 2 raised to power -1 will be 1 time, I don't want to, this will be, this will be 1 over 2. This one will be 1 over 2 square, which is 4. This one will be 1 over 8. So let's multiply out on our right. 1 times 1 over 2, that would be, I don't know whether to leave it decimal or fraction. Well, 1 over 2 plus 0 plus 1 over 8. I'm just doing, not even secondary, primary school maths. Dr. Woyi sitting down doing primary school maths. Now, under the LCM is 8. 8 divided by 2 is 4. Plus, this is 0. Plus, this is 1. So, we get 5 over 8. I hope there was no mistake. So, we get 5 over 8. That's the answer. Correct me if there's a place I made a mistake, please. If I made a mistake, correct me. Okay, I can see someone clapping on Zoom. That means I did not make a mistake. If you want to convert 5 over 8 to decimal, you do. So it depends on what the answer options are. If the answer options are in decimal, then wahala day. You have to convert to decimal. Okay, we are done. So another assignment I'll leave you. I said we should note it. Someone wrote 1001. So let me use red and write here 1, 0, 0, 1. Point, 1, 0, 1. How do you convert this? Left-hand side is the whole number part. Right-hand side is the fraction side. So you convert the whole number, the fraction, the way we did it. In fact, this is like this. Just the way we did it, here will be 0, 1, 2, 3. This 2 raised to power 3. 2 raised to power 2. 2 raised to power 1. 2 raised to power 0. 2 raised to power, 2 raised to power -1. 2 raised to power -2. And 2 raised to power -3. You multiply, add. Red times purple plus red times purple plus red times purple plus red times purple. You add everything. And you might get, as we got, 9 points, that fraction, 5 over 8. 5 over 8 should be 0.6 something. 625. So I'm leaving my whiteboard, going back to the slide to finish the 2 remaining slides there. At least we have time to do that. Okay. I want to check to see whether anybody is saying side it is wrong. Okay, I'm writing on Fulari. So I am closing this. Wahala now to close this whiteboard. Okay, let me see. Yeah, it's closed. So we go back to our screen. So what we have done is what is written here. What you are seeing on the screen, that's all we have done. The grammar. I tried to explain what we did. So if you still could not understand the problems we solve now, read this and see whether it could help you. And this is the one I told you to take home or take hostel if you are staying in the hostel, or take squatting if you are squatting, or take under bridge if you are, let me leave it that way. Now, I come to that again. That's the table. I brought it here not to say anything, but for you to have it. When you get the slide, you can expand, or at this age, unlike when I was a student. When I was in primary school, there was no mobile phone. So you can imagine. I'm not too old though, I'm still 16 years old. But when I was in primary school, there was no phone. When I entered secondary school, there was no phone, but when I was entering SS2, SS3, Nokia phones came out. And in our house, the whole house, we had one Nokia phone that my daddy would always keep at the middle of the parlor. Go and touch it now if they born you well. So from there, when I traveled out to do university, I met a country where everybody was using mobile phones, and I knew where I was coming from. We had just phone in the parlor. What happened? Everybody's using phone. No, I called my dad, Daddy, please, I need a phone. You will understand his reaction. In the house, everybody's using one phone, and you want to have one phone. So he was reluctant, but I made it known to him that it was normal something here. Then finally, I got a phone. What am I saying? Today, all of you have phone. You don't know how it all started. You are using phone anyhow. You see phone, you still start using it. There was a time nothing to steal, talk less of having it. And since you have phone, sure you have internet connection. Nokia phone doesn't know anything about internet. So having phone is one wahala. Another thing is having the internet. So with the internet, ladies and gentlemen, you can kukuma go in and type ASCII table as you are seeing on your screen. You will see it clearer. But I'm explaining to you what it is. It is a table that assigns numeric values to alphabets. Capital A has a different code. Small letter A has a different code. So look at the next slide, what I'm showing you there. Look at it very well. Numbers, combinations, they have their code. You are not seeing anything binary here. You are not. So any number there can be converted to binary. All right. No, I did not live in the Stone Age. I did not live in medieval age. I lived in your own age. Didn't you see me in secondary school when you guys were doing secondary school? Okay, I remember now. Most of you went through special centers. That's why we are seeing 300 and something in JAMB. Oh yeah, now we'll see as exam results starts coming out. All right. Thank you, beautiful ladies and gentlemen. Thank you for listening. Thank you for coming around. Thank you for your questions. Thank you for everything. And I wish you all the best. So I will be alerting Dr. Lucky to get ready for you guys next week. So, and I will tell Dr. Gray to add him in that is it course rep group where he'll be sharing his materials. So today I will share the slide and the recording. And I hope we are getting our manuals. Please get them. If you don't have money, do you know what to do? Don't eat today. Your meal for today can buy that manual 3 times. Don't eat today, go and buy the manual. read my lips. Go and buy the manuals. There is a deadline. Once I think exams have ended or so, can't remember, or before that, you are wasting your time if you want to come and submit. I know you guys will be communicated if you have not been communicated already, but you'll be communicated on how to submit. It will not be 111 each person coming to computer science department. No, it's going to be like a course rep we collect. And the course rep, please, will make sure you have the list of those submitting, because tomorrow, one Michael or one Aisha will come and say, don't you remember I submitted? When in fact, they never bought stocklets of submitting. And the blame will be on your head. When they get D and they can't cross over TJ Araba, or they get E and it brings down their CGPA, that's where you now see enmity will start, and you guys should be enemies till the end of your stay in Unilag. So always have your, we call it attendance if you like, list of your classmates that submitted. Let them sign that they have submitted, and those that did not submit, they will not sign. You are going to submit it at the computer science department, have your copy, so that when fight one starts, you bring it out and say, Oga, you did not submit. Madam, you did not submit. All right, thank you very much. Have a great day. Enjoy your stay in Unilag. Bye-bye.